Alright, this video is going to cover Chapter 10. We're in Part 2. And in Part 2, we're essentially looking at muscle contractions on a larger scale. In Part 1, we primarily focused on the structure of the muscle, both as a whole and at the cellular level. And then we focused on a muscle contraction in a single sarcomere. Okay, now you have to remember that there's lots and lots and lots of sarcomeres on one myofibril. There's many myofibrils within a muscle fiber, and there's many muscle fibers within an actual muscle. And so we looked at it on a very small scale. Part 2 is going to look at muscle contraction in terms of the whole muscle, or just on a larger scale. And so we're going to start with a muscle twitch. And a muscle twitch is just a very brief single cycle that involves a contraction and relaxation. So this is not really going to allow us to do any work. It's just a single contract and relax going on. And so this is going to be produced by a single action potential in a motor neuron. Now you do need to remember that motor neurons can actually stimulate multiple nerve fibers, and so we call that a motor unit. The motor neuron and all of the fibers that it actually innervates together is a motor unit. So when you have this single action potential, it's going to create a contraction in each of those muscle fibers in that motor unit. Now, there are different sizes of motor units. We'll actually come back to this here in a little bit, but you could have a smaller motor unit that just innervates a few muscle fibers, or you could have a much larger motor unit that is going to innervate many more muscle fibers. Now, usually your small muscle, anything that's delicate and precise is going to be a smaller motor unit. Things like, your fine motor skills, like with your fingers and things like that. Whereas your large motor units are going to be more responsible for like your bigger movements, like moving your legs and your thighs, things like that. Now, we have seen a lot of graphs in the nervous system, and in this lesson you're going to see a lot of graphs as well. But something I want to point out, because they're very similar, but in a lot of our nervous system graphs, we were looking at voltage across the membrane. Now we're going to have a correlation between the voltage of the action potential and the tension in a muscle. So every graph that we're looking at in this lesson is based on a force. Okay, so when we look at a muscle graph, the y-axis is how much force or tension there was in that muscle. And so contractions are going to lead to greater tension. And so in a muscle twitch, there's kind of three phases. You have the lag phase, which is here. You can see in the beginning there's not a lot of tension there, and this is the time that it's taking for that muscle to get excited. So we had the excitation contraction phases, and so essentially this is the time between when the stimulus is actually applied to when that contraction actually begins. And so what's going on in this particular phase is that action potential has reached the muscle cell. It has triggered calcium to be released, and that action potential in the muscle is going to be triggered. So this is just kind of that excitatory phase. Now the actual contraction phase is going to begin once that tropomyosin is shifted and those myosin heads attach, and we have the formation of those cross bridges. We have that power stroke going on. And so in this contraction phase, we have that kind of cross bridge cycle where those myosin heads are attaching and pulling, detaching, recocking, attaching and pulling, and so forth. So you can actually have those cross bridge cycles happening many times. And as you can see, the tension in that muscle is increasing. And then you have the relaxation phase, which is essentially going to be the opposite of your contraction. Remember that calcium is going to be pumped back into the sarcoplasmic reticulum. The tropomyosin is going to be moved back into place, and that cross-bridge cycling is going to stop. And so that you can see in the graph that tension is going to go back to 0. Okay. So just to kind of do a quick comparison, in an action potential, it is electrochemical. That's where you have that electrical impulse, whereas the muscle contraction is an actual mechanical event. The muscle is moving or physically contracting. We measure the action potential in millivolts. Over here you can see your voltage, whereas in muscles we're measuring it as a force or tension. And an action potential is going to be faster than your actual muscle contraction. It takes time for that muscle contraction to occur after that action potential has reached that synapse. All right, so we're actually going to cover objective 6 in this video too, and so you're going to see some similarities to this in your nervous system notes, but there's, like we mentioned earlier, there's a wide range of motor units. There are small motor units and there are large motor units, and by having a variation in our motor units, that's going to give us a wide range of control over our muscles. And so if we have smaller types of activities, if I want to pick up something very light, that maybe require small motor units. And so they're going to be a lower threshold, they're going to be more excitable, and so these are going to be the first motor units that are going to contract, and they do result in a small degree of tension. Whereas your larger motor units are going to have higher threshold, they're going to have more muscle fibers involved, and these are going to activate your larger muscle fibers, but that force is going to be much, much higher. Once again, think about it in terms of your smaller muscles, like in your delicate types of movement, like in your hands versus your legs, okay? So definitely going to give us a wide range of muscle control. And so just like we talked about in the nervous system, just like action potentials can vary in strength and stimuli can vary in strength, the strength of our muscle contractions can vary. We can have weak contractions or we can have strong contractions. So just like we saw with stimuli, our muscle contractions can be graded, which means they occur at different levels. So if you're picking up a feather versus picking up a giant weight, there's going to be different levels of force that are required for that, and therefore our muscles are going to respond in a graded fashion. And so let's say we need to pick up something heavier. You know, how is it that we go from trying to pick up something very light to something very heavy? Well, there's two ways that we can increase the force of a muscle contraction. We're going to look at summation, which is where we add forces together, and we're going to look at recruitment, where you recruit other motor units to help out. And so both of these are going to help make those contractions stronger over time. And so in summation, just like the word means, if you sum something, you are adding it together. This is where, as you have stimuli that are continuously coming in, so here you have each of these humps represents a new stimulus coming in. So as you have stimuli that are coming in before that muscle is completely relaxed, what happens is those forces are added together, and you can see that as a whole, that contraction force is increasing. So that's going to be summation. And so when you have new stimuli coming in, that second twitch is going to be stronger than the first twitch, and then that third twitch will be stronger than the second because you're kind of adding them together. Okay, so the successive signaling is going to be added together, which means that force is going to increase. And then with more stimulation, summation and muscle tension are going to rise. Now there is going to be a max point where it can't really go any higher, but by adding those forces together and by adding those stimuli together, we're going to see an increase in that muscle tension. So a couple examples where you can see this is something called TREP, and this literally means steps, and so you can kind of see the stepping in that graph. And so if you have a rested muscle, it takes a little bit for it to get going. You know, think about when you roll out of the bed in the morning, a lot of times you're not up and at 'em and super energetic. You kind of have to build up to that energy. It's kind of the same way in your muscles. So when they've been rested for a while and they initially get stimulated, those contractions are not going to be super strong. But as those forces or those stimuli are coming in, what's going to happen is the muscle tension is going to increase in a graded manner. So as those contractions are happening, they are going to increase in that tension. And so that's what we call the TREP. Now once again, there's going to be a max, okay, but you can see that the stimuli are not super frequent, and so that muscle is able to kind of contract and relax, but your successive contractions are getting stronger and stronger. Now we also have tetanus, and tetanus is where the muscle is going to be stimulated at a higher frequency, and so what happens is they don't always have as much time to relax in between contractions. So we could look at it in terms of incomplete or complete tetanus. In incomplete, they do have little short periods of relaxation before they're stimulated again. You can still see that TREP going on. You can see that steady increase over time, but they're kind of like short contraction and relaxation phases. Those relaxation phases, notice they're not going all the way back down. And so we're building tension, but we have these very small relax phases in between, and that's what we call incomplete tetanus. Now, when the stimulus frequency is super high, then the muscle doesn't even have time to relax at all. And so this is where we get complete tetanus. And this actually allows for smooth, efficient movement. Okay, so you have a high frequency stimulus, and so there's not even any time to relax at all. And notice we are at that max tension. Okay, so all of these kind of go along with that summation. So here you see a single twitch. Here you see the adding together of those twitches. Here you see incomplete tetanus. We're reaching that max, but there's still small levels of relaxation. Or we have complete tetanus where they're pretty much at their max without any relaxation phase at all. And so just kind of a quick comparison, TREP occurs when the stimulus is high, but it's low frequency. So like the strength of the stimulus is high, but they're not happening back to back to back to back. So there's some time period for that short relaxation phase. And then tetanus is when the stimulus is strong, it's max, but they're also high frequency. And so you have those shorter relaxation phases or no relaxation phase at all. And then just to kind of tie this into something you may know, you've probably heard of tetanus before. Now, tetanus in terms of muscles is actually a good thing, but tetanus in terms of the disease is actually not good at all. This is when you have prolonged contractions of muscle fibers. And so this is caused by a bacteria called Clostridium tetani, and it actually produces a neurotoxin. So this is a toxin that affects the nervous system. And so what happens is it causes those muscle contractions to stay contracted. And so it can start with lockjaw, and then the body kind of seizes up like you see here in the picture. The muscles become very rigid. It can cause spasms, and then those can lead to further complications, which is why if you step on a rusty nail or do something like that, you need to go get your tetanus shot, because it could be very serious. It's easily treatable and it's preventable, but if you don't treat it, it could actually be deadly, because if your muscles aren't working, that's going to affect your heart, and that's also going to affect your respiration, and so both of those could lead to death. So I don't want you to confuse this tetanus, which is bad, with good tetanus, which is controlled muscle movement. All right, and so what we've talked about so far is kind of summation, and so now we're going to look at the other way that we can increase muscle tension, and that's going to be recruitment. And essentially what's going to happen is we are going to recruit more muscle fibers. And so as you need more and more strength to do something, there's going to be an increase in the activation of motor units. So remember that those smaller motor units are going to kick in first, but as the muscles realize that they need more force, then other motor units are going to be recruited. And so the more the motor units are recruited, the contraction is going to get progressively stronger. So not all motor units are firing at all times, even on a strong force. Normally they kind of take a break. Some are going to rest while others are actually active. And that allows for kind of longer muscle contractions. It is possible to max out your motor units, but that cannot go for very long because it requires way too much energy. So, but when we need it, like you hear of people doing crazy things, you know, like lifting vehicles and stuff like that. So sometimes in times of stress, with the help of adrenaline, we can kind of max out those muscle forces and really put them to work. But that's not something that you can sustain for a very long period of time. And so like what you can see here is like your small motor units, they're going to be responsible for smaller movements. And then your larger motor units are going to be required for larger movements. But as more are needed, more motor units will be added, and that's going to lead to a stronger contraction. Now this is something that should look familiar too, because it was very similar. This is very similar to what we saw in the nervous system. And so here we have stimulus types. And so just like in the nervous system, we have to meet thresholds. So if you have a subthreshold stimulus, that means it's not going to be strong enough to trigger an action potential. And so a subthreshold stimulus will lead to no contraction. If you meet threshold, it will generate a contraction, but it's only going to generate a contraction in a single motor unit. You can do more motor units, okay, and that would be your submaximal. Or you could essentially produce action potentials that are strong enough in axons of all of the motor units. And this is where you're literally going to max out the max capacity of that muscle. So even if you had a stronger stimulus, that muscle's maxed out. We are already triggering all those motor units at once, and so we can't really get any higher. And so we've seen graphs like this for the nervous system. Once again, notice we have tension over here instead of voltage. But subthreshold, you get no muscle contraction. So here's your action potential graph, and here's your muscle graph. So if we're not meeting threshold, no muscle contraction. If we're barely meeting threshold, you can see it's a very weak single contraction. And then as we increase that stimulus, ultimately we'll get to our max. But with different stimuli come different contractions. All right, we're going to stop there for this video, and we'll come back and do a video for Objective 7.